Right. See, if an aldehyde reacts with an alcohol, you will get a new compound called acetal. But for that to happen, you cannot take anything in aqueous solution. You have to take it in dry HCl. The mechanism proceeds like this, where an aldehyde or a keto group will take H plus from dry HCl, and that activates or increases the positive charge on carbon. And from there, alcohol as a nucleophile will attack. So you will get OH and OR group, geminally aligned OH and OR group, and that is called as hemiacetal. And when this OH group takes H plus, you will get OH2 plus. And OH2 plus is a good leaving group, and that's where the second mole of alcohol can attack, removing out this water molecule, and hence we will get something called acetal form. Okay, this is an extremely reversible reaction. At every point it is reversible, so we do not have to make sure we do have to make sure that water in a large quantity is not present, otherwise the reaction will go in the backward direction. Now, hemiacetals, if you try to isolate them, it has to be done without any intervention of acidic or basic medium. Hemiacetals are highly unstable both in acidic and basic medium, while acetals are still very stable in basic medium but unstable in acidic medium. Okay. For example, if you take this ketone, take 2 moles of alcohol in the presence of dry HCl, you will get this product formation. Now notice, in this case we are breaking one pi bond here, we are making one sigma bond here, and doing that we are making two sigma bonds, correct? Clear? So if you want to make two sigma bonds, breaking these two bonds, then the amount of energy required or released will be almost same. So we can say the delta H is hardly changing. So we can say delta H hardly changes in this case, and delta H of the reaction is not observed. So the spontaneity of the reaction mainly depends on delta S value, because delta H is not a contributing factor. So it is only the delta S which is contributing. Okay. Which means you can ignore this factor. So just check out how delta S is operating. Have you noticed on the reactant side we have 3 moles, product side I have only 2 moles, which means entropy is decreasing. So if delta S is negative, negative and negative will become positive. That's why this reaction is non-spontaneous. That's why you will see this reaction is actually a non-spontaneous form. Okay. And you will notice that ketones usually does not give acetals that easily. But we can change that by, instead of taking 2 moles of alcohols, we can take just 1 mole of glycol. Okay. So this way it helps in two ways. One, the entropy factor is taken care of, because now the reactants and products will have same number of moles. Second, it will now become a cyclic structure, so chelation will always favor the reaction in the forward direction. Got it? So in two ways it will help. One, it will try to compensate the entropy factor, and second, increasing the chelating nature. So this way the reaction go in the forward direction. Clear, beta? See, this cyclic acetal preparation will really help in uh, protecting aldehyde or a ketone group whenever it is necessary. For instance, if you have, there are 2 ketone groups and I react with a glycol, So one of the position will get an cyclic acetal formation. Okay. And now when you react with lithium aluminum hydride, which is pretty much in a basic form, this is in a basic form, and this one is also in a basic form, which is Clemens's reduction, Wolff-Kishner reduction. So with lithium aluminum hydride, this keto group will reduce into alcohol. Same with NaBH4, and last with NH2NH2, that will convert keto group into alkane group. You can see that is becoming alkane. So what you notice is that this part is getting protected because that will not undergo any kind of reduction. And thereafter again you bring back in an acidic medium. So this part will convert back into keto form. So you can see here again you will get keto form back. So typically this protecting nature is what is more useful when it comes to acetal formation. Clear? Right. Now, the next type of reactions are mainly based on tautomerism. Okay, all condensation reactions, aldol type of reactions, they are all dependent on tautomeric nature of aldehydes and ketones. We know that aldehydes and ketones will always maintain an equilibrium with enols. Okay, and this equilibrium could shift in the forward direction if the enol content is getting more stabilized. Okay, usually in these kind of cases, like this one and this one, you will notice the percentage enol is almost 100%. That means the reactant side, the keto part hardly exists. It mainly exists in their enol part. What is their enol part, respective enol part? You see, first one is this one. This is the enol form, which we call it as phenol. And second one, OH, this one. This is also a keto form. I mean, enol form. This one is also keto form, like this. I mean, enol form. So these are the respective enol forms, right? And they are more stable in this case. Now, if you compare the percentage enol, it will be greater than 50 percentage. Okay. So check it out. First, and simple aldehyde, dialdehyde, and beta ketoaldehyde, beta ketones, diketones, beta esters, and beta diesters. As you keep going around, you will see these three groups have enol content greater than 50 percentage. But by the time as you reach towards ketone or diketone, by the time you reach towards ester or diesters, the percentage enol decreases drastically. Okay. And moreover, tautomerism is more easily observed in basic medium as compared to that of acidic medium. Okay. Let me show you the mechanism also for that. For example, if you have any keto group like this with OH minus, the OH minus will take H plus from here. It will become enolate ion like this. And the resonating structure for this one will be O minus and double bond. So this is called enolate ion. This is enolate ion. Now, this enolate ion is the one which will take H2O, I mean H plus, and sorry, here. This will take O minus will take H plus, and you'll get OH and double bond. What is this one now? Enol. Okay. If you take it in an acidic medium, right? In acidic medium, the lone pair will take H plus. This is the one which you will get. And then H2O. What is the resonating form for this one? The resonating form for this one is simply OH here with a positive charge. And on this OH with plus charge here, H2O as a base will take H plus from here. Taking that, you will get a double bond plus H3O plus. Now, see the difference in basic medium and see the difference in acidic medium. Okay? Let me show you one difference. In basic medium, in case of basic medium, you will see there is an enolate ion forming, correct? There is an enolate ion forming. Clear? While here, if you notice, there is an enol type of compound form with a positive charge. Here, octet is always complete in all the positions. Here, octet is incomplete on this carbon position, isn't it? So, which means between these two, if you compare the stability, obviously the enolate ion is more stable. This is factor number one. Now, the second factor is water as a base can extract H plus from here to get a double bond, correct? But here you are using OH minus to extract the H plus. Which one is a stronger base? Obviously, OH minus is a stronger base here. Okay, 1 second. Just a second. So you will notice that if you compare an enolate ion and an enol form, then enol is less stable, enolate ion is more stable form. So that's the reason why the base catalyzed mechanism is more observed, or rather I would say more easily observed as compared to that of acid catalyzed mechanism. Okay. Next thing is tautomerism always shows kinetic isotopic effect. What do you mean by that? If you have this ketone, for instance, you react with basic group like OD minus in the presence of D2O. And during the mechanism, you know that you will get an enolate ion like this double bond O. You can get minus here once, and you can get minus on left hand side once, correct? So wherever the negative charge is coming across, at those points you can get deuterium getting exchanged. Okay, so as many hydrogens we have, those all will get exchanged by deuterium. Clear, beta? So notice, in every form of it, you should know how many deuteriums are getting exchanged. For example, in this case, okay, you know that this is the position where there are two hydrogens which can be exchanged. This is a position where we can have deuterium which is getting exchanged, because you need to check out the negative charge is getting resonance stabilized or not. So you can see it is getting resonance stabilized here. And during the resonance here also the negative charge will come. So you have to exchange deuterium here also, here and here. So on exchanging at three positions, what is the number of deuteriums you will get? 5. Okay. Same way, when you have this case, these two positions you can exchange two deuteriums. This is the position you can exchange. This is the position you can exchange. So total 4 deuteriums you can exchange. In case of phenol, phenol is more of an enol form. So in the enol form, if you notice, this hydrogen get exchanged, this deuterium here, here, and here. I mean, all these 4 positions, hydrogen is going to get exchanged by deuterium. Okay. Here also, these three hydrogens will get exchanged. These three hydrogens will get exchanged. And while here the exchange is happening, you will get an enolate ion here with a minus charge, which can push here, and pi bond will be pushed here. So negative charge crops up here also. So at that position also, you need to exchange with deuterium. Okay. So total, we will have 7 deuteriums getting exchanged. Here, these three hydrogens, and most importantly, these 2 hydrogens also. Total 8 hydrogens getting replaced. Clear? Right. Now, let us understand two major reactions of aldehydes and ketones. One is Cannizzaro reaction, the other one is aldol reaction. Okay. See, Cannizzaro reaction is observed only for aldehydes with no alpha present on it. Okay. Which are those cases where there is no alpha present? Okay. But only this case is present like this. HCHO, then benzaldehyde. Okay. CHO like this. Okay. Which is called as furfural. This is called furfural. Correct. Or you can have CHO, this one also. Clear? See, this is the only exception where we have carbon having hydrogen here with CHO like this. So there is a alpha hydrogen, but yet it will give, and this will still going to give you Cannizzaro reaction. Okay. So Cannizzaro is observed in this case, this case, this case, this case. Along with that, you will also see here Cannizzaro is observed. Okay. It usually undergoes a disproportionation reaction. Cannizzaro undergoes a disproportionation reaction. Okay. What is disproportionation? Just like in redox, we can have same molecule undergoing oxidation as well as reduction. Okay. Let me show you this example here. For example, if you notice this one, here when you have HCHO, H, C double bond O and H, you see carbon is losing 2 electrons to oxygen, gaining 1 electron from here and gaining 1 electron from here. So that makes the oxidation state of carbon as 0. And from 0, as it gets oxidized, as it gets disproportionated, one, it is forming an alcohol like this, OH. The other one, what it is forming is acidic group, which is O minus, like this. Okay. So now, if you notice the oxidation state here, carbon is gaining 3 electrons from 3 hydrogens and losing 1 to oxygen. So it is like minus 3 plus 1, which makes it minus 2. And here carbon will make, you know, plus 3 toward, because it is losing towards 3 oxygens, and plus 1 from carbon. So it is minus 1 from hydrogen and plus 3 from oxygens. So that makes it plus 2. So have you noticed from 0, oxidation state 0, it is getting reduced to minus 2. It is getting oxidized to plus 2. So that's how there is an oxidation reduction as well as oxidation both happening. Hence, Cannizzaro is a disproportionation reaction. Okay. And Cannizzaro is usually operated only at high concentration conditions. Okay. That means if you take NaOH or KOH over and above 50% of the concentration, then the reactions are feasible. See, if I take 2 moles of aldehyde with 50% of NaOH, 1 mole of aldehyde will convert into an acidic form and the other mole will convert into an methanol form. Similarly, if I take 2 moles of benzaldehyde, 1 mole will convert into PHCO minus and the other mole converts into alcohol. So let us see how the reaction mechanism works. See, if at all we are talking about the formaldehyde, the OH minus will first go and attack on this carbon. So you will get this as O minus, OH and H will be present. And here this O minus will try to make it into a double bond form, and the H minus from this group is being removed. The H minus will go attack on the second mole of the aldehyde. Okay. Now you might wonder, sir, how is this favoring? See, first the carbon here has sufficient delta positive. Secondly, this O minus is a strong plus I group, and this strong plus I group is the reason why it is pushing its electrons to make a double bond back and remove H minus. But since this will take a lot of time, this is the rate determining step as well. So this H minus go and combine with the second mole of the carbon, and therefore the first mole here, so this is the first mole, this is the second mole. The first mole is converting into an acidic group, second mole is converting into an alcohol group. And you can see from the second mole, once you get an alkoxide CH3O minus, that O minus will eventually take H plus, convert into an alcohol, while HCOO minus is the remaining part what you have. Okay. So this is the mechanism which is observed. Now, since this is a rate determining step, this is the rate determining step, it depends upon concentration of this aldehyde and depends upon this intermediate also. So where is this intermediate coming from? The intermediate is coming from OH minus and this, isn't it? So I can replace this intermediate with respect to some constant into these two factors. So that's how you will get 2 moles of aldehyde square and 1 mole of OH minus square. I mean OH minus power 1. So that's how you will have rate in this form, which is a third degree order or third order kinetic reaction. Okay. In this case also, primary isotopic effect is observed. Why? If you notice the rate determining step, the hydrogen is being removed. So if by chance there is a deuterium here, the reaction will become even slower, quite slow reaction. Okay. So which means H, if you have only hydrogens, the reaction rate is better compared to deuterium, compared to tritium. Okay. Now, if the concentration of NaOH is taken quite sufficiently high, in that case, this first intermediate which is forming, which is HCOH, H and O minus, now this can again interact with OH minus. OH minus as a base can take this H also. You can get 2 O minus. And 2 O minus has an advantage because from both end it will support plus I. Therefore, removing H minus becomes easier. So this is a better hydride donor. If the question is only about hydride donor, okay, okay, hydride donor, like which one is a better hydride donor, then definitely HCO minus, O minus and H. This can provide hydride way better than HCO minus, OH and H. Okay. So hydride donor requires to have lot of donating groups on the carbon position here. So more donating groups, better the hydride donor form. Another example, if you have a benzaldehyde with O minus, H and OH, this is benzaldehyde form. If there is a donating group, it is a better hydride donor compared to this one, and compared to withdrawing group, O minus, H and OH with NO2. If you have it with NO2, it is a very bad hydride donor. Okay. So remember, this order is only for hydride donor and does not tell anything about the rate of the reaction. Okay. Mm. Now you notice, if this is the better hydride donor, then obviously H from here will attack, convert that into acidic group and alpha oxide group. Now what will be the rate? Because you have used 2 moles of OH minus, now it will be OH minus twice, and the order of the reaction will be 4. So this is one thing you need to understand. If your concentration is around 50 degrees of NaOH, okay, 50% of NaOH, then we will see third order reaction. But if it is more than 50% NaOH, very high concentration taken, then you will see the order of the reaction is 4. Okay. And next, suppose if you have a cross Cannizzaro, that means a Cannizzaro which is happening between two different types of aldehydes. In that case, the one which is more reactive, in this case, you know that reactivity of formaldehyde is more than benzaldehyde, because benzaldehyde is naturally stabilized by the resonance. So this reactivity of aldehyde is less. Here the reactivity is more. So whichever the aldehyde is more reactive, that will convert into acidic form. The one which is only, which is less reactive, that will convert into an alcohol form. Okay. So this is something which you need to keep that in mind, that it will favor more of alcohol form for less reactivity, acidic form for more reactivity. Okay. Now, which of these cases will give you Cannizzaro? You can see, although this is an aldehyde, but because from nitrogen end it is extremely strong donating group, the nucleophilic addition is hardly observed here. That's why, since nucleophilic addition is less favorable, this reaction is not going to observe in Cannizzaro if you have such strong donating groups. This, I told you, is an exception, only happening when you have high concentration of NaOH. This will make a reaction, 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 because here the alpha hydrogen is on sp3 carbon. If it is sp3 carbon, it is, it is of no use. Even if it is there or not, it doesn't matter. Cannizzaro will take place in this case. Now CCl3CHO, this is an haloform reaction. In haloform reaction, what you will notice is, if you have C double bond OH, as the OH minus goes and attacks here first, so you will notice that this will become Cl thrice C, this is O minus, H and OH. Then as it closes here, it is not the H minus which will come, it is the CCl3 minus that will come out. So basically what you will get is CCl3 minus plus HCOOH, and this will take away H plus and convert into CHCl3, which is halo form, and CO minus. So basically this will go in the direction of halo form reaction and not in Cannizzaro. Okay. That's clear, beta? Right.
Yes.
Okay. Lastly, if you have a propanone here, although there is a alpha hydrogen here, there is alpha hydrogen here, but that does not help in any reaction here. As OH minus attacks, the bond itself will open up. This bond will open up and you'll get a minus charge here and OH here. And this minus charge will take H plus from here. This will become an CO minus and CH3 here. Okay. So here there is no alcohol formation. You will get this as CH3. CH2, COO minus. Only an acid is forming. Okay. Now see, in CaNi0, if there is hydrogen and deuterium, both are present, then you know that H minus is a better donor group. So H minus will go from here, from first mole. So leftover will be deuterium here. So therefore, this is one product. The other product H is getting shifted, so this will become CH2DOH. Okay. So to show you, let me show how and which one will happen. C double bond OD here, which I can write it as CO minus and OH, and here D C double bond OH. So as this closes, this is the H minus which will shift here. Okay. So that's how you are getting these products. First case is clear, beta. CaNi0 reactions, first case is clear. Let's see the second case. If you have NaOD, here OD minus can connect here, right? And thereafter H minus will be relieved and you will get CH3OD here, and this will become HCO minus here. If you have a cross CaNi0 between these two aldehydes, obviously formaldehyde is more reactive. So the more reactive one will become acid, the less reactive one will become alcohol. Okay, here also this one is less reactive, this one is more reactive. So the one which is more reactive will become acid, the one which is less reactive will become alcohol. Okay, now notice this one. If you have PCH2CHO and then I have 3 moles of HCHO. Okay, right. Okay, I'll come to this reaction because before that I need to discuss aldol. Let me come back to those three reactions. Uh, because without aldol, I think that is one reaction which is, yeah, which I need to discuss that. So check it out. First, let us go and understand the second type of important mechanism, which is aldol. Okay. I think the CaNi0 type is clear. There is a hydride shift. It is becoming disproportionation reaction. So I hope that fundamental is clear. Okay. Now, what is an aldol reaction? And aldol, what is the important condition? See, for aldol, this is the opposite conditions of aldehydes and ketones. The first condition is must have alpha hydrogen. Second condition is use dilute base, dilute base as OH minus. Okay. Okay. Also observed in acidic medium also. While CaNi0 is not observed in acidic medium, here it can be observed in acidic medium also. These three are the important conditions for aldol. Okay. Aldol, just like CaNi0, which has self as well as cross CaNi0, here also we will have self aldol and cross aldol as well. Okay. So notice, if I take 2 moles of an aldehyde here, just like in CaNi0, here also we are taking 2 moles of an aldehyde. But these are those aldehydes which has an alpha hydrogen. You can see there are 3 alpha hydrogens here. Now, how does the mechanism take place? See, first OH minus will take away this H plus via tautomerism, converts into enolate ion. And it is the enolate ion which will act like a nucleophile, and that nucleophilic carbon will attack on the second mole of the carbon. And as it attacks, you will notice this will convert into this O minus form, and O minus will take H plus from water. You will get into this particular form. Now, What do you name it here? The name here is actually beta hydroxy aldehyde or ketone, right? Beta hydroxy aldehyde. So basically, it is an aldehyde combined with an alcohol. That is why it is called as aldol. Okay. And at a beta position, you have a OH which is a very weak leaving group, right? When you have weak leaving group and you have a base here, so base will definitely try to extract proton from this beta position. From this beta position, I mean from this alpha position, it will take the H plus, and because of which at this beta position, which has a leaving group here, OH minus can leave because O minus will form, C minus will form here. Complete carb anion will form, which is a conjugate base. And this conjugate base can push the electrons to make a double bond, leaving the OH minus, and thus we can get double bond here. So the double bonded group is called condensed aldol. Okay, this is the condensed aldol. Okay. Now this mechanism type where the OH minus is first taking H plus and thereafter carb anion is forming which is pushing. This is called E1CB mechanism, isn't it? Because first the carb anion is forming, conjugate base is forming, and that is pushing out the electrons to remove OH minus. Okay, clear everybody? Right. So now see the rate. Rate of the reaction depends upon this one, this step, right? This is the RDS of the reaction. So for this RDS, what you will notice is first, this enolate is a part of this aldehyde and OH minus. So one aldehyde, one OH minus. And now you have a second aldehyde also. So multiply another aldehyde. So that's why you will see the order of the reaction is 3. Correct? The order of the reaction is 3 here. So rate, no, sorry, this is one important part. If you are taking at a dilute NaOH, the first step is the rate determining step because the formation of enolate itself is going to take a time. But if you are taking in a concentrated form, then the second step will become the enolate ion. I mean, second step will become the rate determining step. So, if you take a dilute NaOH, then you will see isotopic effect observed. Whether you are taking H, D, or T, the rate will change. But if you are talking about the second step, then in this case, there is no hydrogen being removed, right? In this case, between these two, there is no hydrogen removal or hydrogen is being moved. So therefore, the rate will not change in the second step. So order varies. Order can become 2 or order can become 3 depending upon whether you're taking concentrated NaOH or dilute NaOH. Okay. So the aldol is clear, beta. See, what is the short way of understanding aldol? See, check out. Imagine I have two moles, CH3CHO and CH3CHO. These are the two moles given and OH minus is given. See what you do. You take one molecule. Let's say this molecule I taken. You write the same way how it is present. CH3 is there. Then CH is there. Just that oxygen which is there, write that into alcohol form. Done. And then say take out the second mole's carbon, alpha carbon. This is the second mole carbon and just connect that with this group as CH2 and CHO. Done. So you can see this part is coming from the second mole, which is this one, and this part is coming from the first mole, which is this one. Clear with the shortcut? So wherever you have, just use the first mole, write it into alcohol, then connect the second mole's alpha position. Okay. See the same way here also, if I take 2 moles of ketones here, First mole will take H plus from here, gets negative charge. That negative charge will connect here, and that's how you'll get the beta hydroxy ketone. Beta hydroxy ketone is what we call it as aldol. Beta hydroxy ketone. This is called aldol, and as you heat, you'll get condensed aldol. If you have this aldehyde with HCHO, now you have an aldehyde which does not have a alpha hydrogen. So obviously that cannot go aldol. So you will mostly notice the cross aldol more, which means CH2 minus from here will attack here, and that's how you will get this as the beta hydroxy ketone. And that on heating will get this as a major product. This is major product. Okay. Any doubt with this aldol case? Check out the number of aldol and condensed aldol forms. Okay. Suppose if you have two different aldehydes, right? This is one aldehyde, this is one aldehyde. If these both are reacting, correct? The cross products are called as Claisen-Schmidt condensation reactions. Claisen-Schmidt condensation reactions. Okay. I showed you short way. Let me show you again. See, for CH3CHO, the same part I am writing CH3CH, only this oxygen I am converting into an alcohol. Then connecting the same mole again from this CH2, I am connecting here, and then CHO, which is this one. So what is this one? This is a self aldol. Similarly, I can write the self aldol here also. First, I'll write CH3, CH2, CHO, CH3, CH3, CHO, and that oxygen I'll convert into alcohol. Now, I'm writing the second mole. Second mole from this carbon I need to connect. So you can see that carbon is connected here. This is the same carbon which I'm connecting. It has CH3 group. Here is that CH3 group. It has a CHO group. Here is that CHO group. Done. So this one is a self aldol. This one is a self aldol. Now if you see the cross aldol, that means this CH2 is connecting here, imagine. So you will get this one. And lastly, if this CH2 is connecting here, then I will get this one. Correct. As the aldol has formed, in the first case there is one chiral center. In the second case there are two chiral centers. Third case also there are two chiral centers. And fourth case I have one chiral center. So which makes if there are two chiral centers, that means four products are possible. Four here, and two here. Total 12 aldol products are observed. Right, beta? We can see 12 aldol products. Now, obviously, if the heating is been provided, you will not expect the aldols to stay like that. They will get condensed. So as they condensed, so this OH and this hydrogen you remove make a double bond. So what do you get? The aldol is called as the alpha beta unsaturated alpha beta unsaturated aldehyde. So an alpha beta unsaturated aldehyde is what we call it as the condensed aldol. Hmm? So you can see this is an alpha beta unsaturated because this is an alpha position, beta position. There is a double bond on those two positions with CHO. And with respect to this double bond, I can have cis and trans isomers. So now again I can get two products. Here also this OH and H if I remove, I'll get a double bond. Again I can get cis and trans. This H and this OH if at all I remove, I'll get a double bond. OH and H I remove, I'll get a double bond. So I'll get 2, 4, 6, 8. So total 8 condensed aldol products. So very important JE question this is. This year it has asked like how many number of aldols can be formed or how many number of condensed aldols can be formed. How much percentage it is, which is major is never going to be asked. You will be asked which is, I mean, how many types of aldols are formed. That is what you need to respond. So you can see 12 if the question is asked only aldol, 8 if the question is asked condensed aldol. Okay, girls, clear beta. Right. What is nitroaldol? Now, nitroaldol is case instead of an aldehyde, at the aldehyde position, if you have a cyanide or a nitro group, then it is called cyanoaldehyde, cyanoaldol or nitroaldol. Suppose you have an aldehyde here and then I have a CH3CN. So OH minus will first take H plus from this carbon, creates CH2 minus, and it is that CH2 minus which will attack. So, and then the aldol will take place. I mean, first you will get this product as CH2OH connected with CH2CN, and that on heating is what you will get it as condensed aldol. Done. Same is the case with the second one also. Now, if you have HCHO and CH3 here, same logic, this OH minus will take H plus from here, it will connect on it and you will get a double bond form. Here also, CH2 minus will go connect on it, you will get this one as a double bond form. Okay, clear? Any doubt in these cases? Okay. I have not written the nitroaldol, but it is one and the same. Let me write down that nitroaldehyde also. So if you have HCHO plus CH3NO2 in the presence of OH minus and heat. So first you will get CH2OH connected with CH2NO2. This will be finally observed as CH2CHNO2. So that's how you'll have nitro uh, condensed aldol. Next, what if I have 2 moles of, aldehydes, correct? Like this. You have already an aldol form of 2 moles and then you are reacting with OH minus. So this can also happen internally where this CH2 minus attacks the second carbon, I mean this aldehyde carbon, and this CH2 can attack on this aldehyde carbon, leading towards this product. And this OH and H can be removed. This OH and H can be removed, double bond can be formed. And as a double bond form, you will get this structure, right? So basically you will get this structure, which you call it as cyclooctatetraene. And we have learned in GOC that cyclooctatetraene is actually non-aromatic, non-aromatic as it does not stay planar. It will adapt a tub-like shape, right? So product what you will get is a non-aromatic COT. COT means cyclooctatetraene. Okay, this is cyclooctatetraene. And next, notice what is intramolecular aldol. So within the molecule, if you have an aldol condition, we can make intramolecular. See, intramolecular is most favorable with this ring size. First 6-membered ring, 5-membered, 7, 4, and 3. Follow this order for intra-aldol. See, here there is a keto group and aldehyde group. And you know that aldehydes are more reactive. So CH2 minus from here will attack here. So you see the ring size 1, 2, 3, 4, 5. So you should be able to get 5-membered ring. So this is also an alpha carbon. It can also connect. If this connects, you'll get 3-membered ring. So considering 3-membered and 5-membered, 5-membered is more stable. So that's why this is the aldol we should look out for. And if by chance this is heated to get a condensed product, so we will get a double bond here and double bond over here. This is the final product. Okay. See the next one. If you have this case here, CH2 minus will be connecting here. So what is the ring size? 1, 2, 3, 4, 5. So it will go for a 5-membered ring here. Now, if you have it this case, check it out. If it connects from this end, what is the ring size? 1, 2, 3, 4, 5, 6, 7. So 7-membered ring. But if it connects from here, 1, 2, 3, 4, 5. So which is favorable? 5-membered ring is favorable. So in this case, this is a connection. In this case, this is the connection. Here internally, you have 1, 2, 3, 4, 5. So 5-membered ring connection here. Here, this is symmetrical molecule. Whether you connect from here to here or here to here, it is one and the same. So it will lead to one 7-membered ring and one 5-membered ring formation. This is a final product you will have. Intramolecular clear beta.
Yes, sir.
Right. Next one is retroaldol. Retroaldol means you are making one aldehyde, sorry, one aldol convert into a other form of aldol. Okay. How do we do that? See, this is an condensed aldol. That means alpha beta unsaturated aldehyde. Okay. So this is alpha beta unsaturated carbonyl group, or in this case, it is keto group. So first convert them into basic aldol in OH minus. So remove this OH, this double bond. You know that this double bond might be formed because of H here and OH here, correct? So try to bring it back. This was the original form. And from here, you know that this is the carbon which must be connecting as CH2 minus, right? So if that is a CH2 minus form, this is that CH2 minus which was connecting here. That's how you got this product. So this must be the original aldehydes, right? This is the original aldehyde form. And now we got a reaction given on this direction. But can it go in other direction also? Yes, indeed. It can go in this direction also. What is that direction? That is from this position as it connects to this carbon, you can get a 3-membered aldol also. So that means from here, you can see it can move on to this side also. So there is an equilibrium that is present between these two. Well, this one 5-membered ring is more stable, but we can see that it can keep converting towards 3-membered ring also. So the existence of these two is called as retroaldol. Girls, clear with retroaldol case?
Yes, sir.
Okay. Why don't we try retroaldol in one more case before I go for the next one? Let me write down here itself as a note. Okay. You both try together. Suppose we have a double bond O here, double bond here with ethyl. This is how the group has been. Okay. Try together. If I need to make a retroaldol for this one, what is the other form of aldol which can go? So what is the first step we will do, beta? Doing simultaneously. So write down the first step. The first step is converting this double bond into, H and OH. These are the groups that must have been present, right? This is how the originally it must have been present. Okay. Thereafter, this is the carbon. See, this is the carbon which is connecting to CH2. I mean, that means this must have been a ketone earlier. So what was the original product, original reactant? The original reactant must have been like this, with this position as a keto group, double bond, with this position as a CH3 group, correct? So this is that same carbon I'm talking about. Is it making sense now? So we got to the original compound. Now, see in the original compound, this carbon connected here. Now, is there any alternative route? Yes, there is. Now, can I say this CH2 minus, which is also an alpha carbon, can go and connect to this carbon? Yes. So let us do that now. So from here, now this carbon, which is CH alpha carbon, this alpha carbon goes and connect here. What is the ring size now? See, 1, 2, 3, 4, 5. So again, it will become a 5-membered ring. Again, you'll get a 5-membered ring wherein it will have one methyl group and one O minus group, correct? Right? And the group from where it is attacking is this one, and then double bond O will be present here. So you can see, I'll make it colored for your understanding. This is the same carbon which was earlier labeled, okay? And the carbon which is connecting is this one. So I'll just take out that color also here. This is the carbon which is connecting, that is this carbon. Check. Clear now? Did you get that? And from here on hydrolysis, you will first get an aldol form, which will be OH, methyl, and double bond O. And this on heating will give you other type of condensed aldol, which is double bond, and this one. So have you noticed? If the question is given to you like this, and the question is asked, what is a retroaldol? Answer should be this one. And the reverse. If ये question दिया है and you were asked what is a retroaldol, answer should be this one. Girls clear? Next, the other type of aldol is acid catalyzed aldol. So far we have noticed everything is base catalyzed aldol. So if I take 2 moles of an aldehyde in acidic medium, you will get an alpha beta unsaturated aldehyde. Okay. So you can notice 2 moles of a ketone, if at all I take in the presence of HCl, right? So the mechanism is pretty much the same here. So we can get one group as, double bond O with a, here you will not have an enolate ion, but you will have an enol. So let me write one as enol, the other one as the keto form as it is, right? In that case, the lone pair from here will push and the pi bond from here will attack the second mole. This is how the mechanism will take place. And now you will have uh, this carbon has two methyl groups and one O minus group here, which is connected with this position. This carbon is now connecting. Let me mark that carbon. This is that connecting carbon, and that carbon will connect, right? And which has one more carbon on it and a double bond O here. Okay, so this is the carbon which is connecting here. Clear it up. And in acidic medium, that will take away the H plus, you will get OH, and you will get this keto form. Now, have you noticed this is a 3-degree alcohol? 3-degree alcohols are very easy to extract in an acidic condition. In an extract acidic condition, getting a stable carbocation. And from there, as soon as we heat it, clear, unheat it, we will get a double bond formation. Done now? And what is the mechanism it is going through now? E1. That is an important difference. So usually when it comes to acid catalase mechanism, E1 mechanism is favorable. In base catalase mechanism, E1 CV mechanism is favorable. Girls, clear it up? Right. The first product what has been formed, this one, is this one. It is called mesitile oxide. Now, if the mesitile oxide is treated with one more mole of aldehyde, one more mole of ketone, now this part of the carbon will also convert into a double bond form, and this is called phorone. Okay, it is forming an aldehyde, aldol on both sides. So that is called phorone. So remember the structures, what is mesitile oxide and what is phorone. Hmm? These are simple JEE mains questions, beta. The question will be asked, how many number of carbons are present in phorone? 1, 2, 3, 4, 5, 6, 7, 8, 9. Clear? Right? Because you are using 3 moles. So 3 moles if you use, you'll get phorone. 2 moles if you use, you'll get mesitile oxide. Now, if at all I use, in case if at all I use 3 moles of acetone but with concentrated H2SO4. In concentrated H2SO4, you will not get any keto form like this. You will directly get mesitylene. Okay. So the group will be like this. See, I have, uh, imagine this way. I will keep an enol form here. One enol here. One enol form here. And one enol form here. Okay. So in this enol form, this pi bond will attack here. This pi bond will attack here. And this pi bond will attack here. And because of this, you will get 3 carbons connecting with each other with one OH group and methyl, one OH group and methyl, and one OH group and methyl. And obviously from here on heating, you will be able to notice a double bond forming in all of them, leaving behind methyl groups. So that's how you will get mesitylene. Clear? Girls, these are very standard questions. So remember, acetone, if you treat with 2 moles of HCl, you will get mesitylene. 3 moles of HCl, you will get 4-on. With concentrated H2SO4, same 3 moles will give you mesitylene. Okay? What is mesetyl oxide, what is 4-on, and what is mesitylene? Remember these 3 cases. Clear now? Right. Okay. Now let me go back to that reaction what I was discussing earlier, which is Tollens reaction. See, check out here. I have an aldehyde. There are 2 different aldehydes here. Here, if you notice, there is an alpha hydrogen. If there is an alpha hydrogen, definitely it will favor aldol first. Okay. And because it will favor aldol first, this CH2 minus will attack here. Correct. Right. So 1 mole of this will convert into an aldehyde. Barabar. This is the first aldol product. This is the first aldol product. Now, if you continue to do that one more time, okay, here there is one more hydrogen. So you react with one more aldehyde here, one more aldehyde here in the presence of OH minus. If you continue to do that, this hydrogen will also be replaced with this alcohol. Methanol will come here also. One more methanol has come, right? This is one methanol which came with the first aldol. Now this is the methanol which came after the second aldol, right? So now we got 2 methanol groups. But what happened here is now this carbon don't have any alpha hydrogen, but you still have further aldehyde present. Now this time there is no other alternative but to go for CaNi0. So in the presence of OH minus, now CaNi0 will happen. In CaNi0, you know that this is more reactive. The more reactive aldehyde will become acid, less reactive will always become alcohol. So this aldehyde will convert into an alcohol form. Now what happened ultimately, we have 3 moles of methanol present on this carbon. So 3 moles of methanol can be represented this way. This is a product forming, right? So girls, what did we notice? We found 2 aldol and 1 CaNi0 happening in the overall reaction. That's how it is consuming 3 moles of aldehydes. What if I start with acetaldehyde? Here it we used benzyl aldehyde, benzyl carbaldehyde. But what if at all I take acetaldehyde? With acetaldehyde, you have 3 hydrogens. So first 3 methanol groups should be forming. This is first aldol, this is second aldol, and this is third aldol. Done? Correct? And thereafter, now this carbon does not have any alpha hydrogen. So when it reacts with the fourth mole, this will convert into an alcohol. You will get this one. And the last carbon will convert into an acid part. How does this look like now? This will look like a swastik form, isn't it? Like this. It does not mean its structure is like swastik. I mean, just the two-dimensional representation can be like a swastik form. And this reaction is called Tollens reaction. Okay, just a second. See the next one. Now here, I have two aldehyde groups here. Okay. In case if you have two aldehyde groups, both of them at benzaldehyde position, Canizero will take place, out of which one will become acid, the other one will become alcohol. Okay, these are intramolecular Canizero, and obviously, whichever is more reactive, that side the acid will form. You know that with respect to this methyl, this aldehyde is more reactive. Here, this is less reactive because CH3 will give you more plus I effect here. So this one become alcohol. But with NO2, you know that this position will become acid, this position will become alcohol. Hmm. Next all are the cases of this intramolecular aldol only. Okay. Next one. What is Tischenko reaction? Tischenko is a very similar Cannizzaro reaction, but here we do have alpha hydrogens. Okay, there is no restriction of alpha hydrogens, and you are not taking a base, you are taking an aluminium salt. Aluminium, you know, triethoxy aluminium form. So if I take triethoxy aluminium form here, correct? So what do we get? You will notice that when we take 2 moles of that, when we take 2 moles of that, these 2 moles will convert into an ester form. Right. So this will form into this ester form. Acha, how does it become? Check. The shortcut is very simple here. When you have 2 moles of aldehyde, you make one thing. You make 1 mole into an acid, you make 1 mole into an alcohol, just like Canizero. Okay. So imagine this mole I convert into an acid, this mole I convert into an alcohol. Once you get an alcohol and acid, make an esterification. Due to esterification, you will get an ester. That's it. Okay. Same logic here. There is an aldehyde here, there is an aldehyde here. Make one aldehyde into acid, one aldehyde into alcohol, and thereafter make a ester. You will get a cyclic ester form. This reaction is called Tischenko reaction. Okay, beta. Next one is benzyl benzylic acid rearrangement. Benzyl benzylic acid rearrangement. Now let's see. Benzyl is having a diketone at the adjacent carbons. This is called benzyl. And in the presence of OH minus, see first OH minus will attack on one position. You will get O minus. Now there is no hydrogen, but there is a phenyl group. Now instead of H minus shifting, this time as it closes, the phenyl will shift onto the next carbon. So same Canizero, except that instead of hydrate shift, now we have a phenyl shift. Girls clear? So phenyl will shift here, you will get O minus, right? And this will become an alcohol, this side it will become an acid. See here, same, there is a double bond O, double bond O here. So one of this group, furan group. Now this is a furan group. The furan group will jump here. So this will convert into an OH minus and COOH. Here also same logic. This phenyl group from here This will jump and attack onto this position. So you'll get 6-membered ring converting into 5-membered ring. Okay. The next one is benzoin condensation. Benzoin condensation is also very similar kind. Check. If you take KCN or NaCN with benzaldehyde, okay, first Cn minus will connect on this C double bond O. You will get cyanohydrin. You know that this is called cyanohydrin. And in cyanohydrin, this hydrogen can be shifted here, bringing the carbon getting negative charge. This happens very slowly, and this is the rate determining step as well. Okay. And this hydrogen got shifted here. Okay. See why that is happening is the C minus can be stabilized by both phenyl ring as well as cyanide ring by resonance. I mean cyanide form with resonance. So that's why this hydrogen can be shifted onto this oxygen, getting a C minus. Now once you get this C minus, we can have this resonance stabilization. So that's why now this C minus is the one which will go and attack on the second mole of benzaldehyde. Okay. Now here it is just like hydride shift, but the hydride shift internally. It is not going to the second molecule. It is happening internal shift. So the hydrogen is shifting from here to here only, creating a nucleophile, and that nucleophile attacks the second mole and generates this one. And once it gets, you know that this O minus will take H plus from here, converts into alcohol, and this will push and remove out the cyanide, get back to its keto form. Okay, so one will become uh, alcoholic group, one will remain ketonic group. So this kind of groups are called benzoin. This is called benzoin, known as benzoin condensation. Girls clear on that? Right. Okay. Right. Now let me discuss about Perkins reaction. Perkin reaction is also very similar to that of aldol. Okay. So where we have this benzaldehyde reacting with an anhydride. When benzaldehyde is reacting with an anhydride, all you need to do is that CH3CO minus, the base which you are using, will take H plus from here, and that CH2 minus will attack here. So how does the reaction show now? Now you'll get PH, CHO minus connecting with CH2, C double bond O, O, C double bond O, CH3. Correct? Now imagine if you do hydrolysis on this one. On hydrolysis, first anhydride will break into acids, correct? And here also it will break into alcohol. So we will get PH, CH, OH. Then we have CH2, COOH plus CH3, COOH. These are the two parts formed. And since you are facilitating this in high temperature, you can get elimination done, and this is the product forming. That's how the mechanism will take place. Clear? And this is called cinnamic acid. This is a very important way of preparing cinnamic acid, known as Perkins reaction. That's clear? Any doubt here? Right. See next one. What happens if you are making a reaction with HNO2? Hmm? If you react with HNO2, right, HNO2 can be generated from NaNO2 plus HCl. So what do we get? Here is at alpha position, you will get NO substitution because this group entirely generates an electrophile NO. Correct? So because it generates electrophile NO, from this position, you will attack on NO, you will get nitro. This is nitroso substitution. And you know that this can undergo tautomerism. This is called oxime. This is an oxime form. And this is oxime. This is nitroso. So you will see nitroso and oxime tautomerism. Let me show you. Like if you have, CH3 N double bond O. This is called nitroso. And if at all I take a hydrogen and shift it onto this oxygen, I'll get this as CH2 double bond N and OH. This is called oxide. So this is how the tautomerism takes place. Just like keto-enol tautomerism, we have nitroso-oxime tautomerism. This is the same product form. Clear? Right. Okay. Now, now there is one case you need to understand. What is KCP versus TCP? Okay. Kinetically driven products or kinetically controlled products versus thermodynamically controlled products. Okay. Suppose if you have a ketone reacting that in the presence of base, you know that this is the enolate forming, right? Generally, tautomerism happens with an enolate form. If I take LDA also, LDA is a very bulky base like this. This is LDA, lithium diisopropyl ammonium. Okay, diisopropyl amine. That is called LDA. So in both cases, these are bases. So they will extract H plus, right? But the extracting of H plus becomes different if there is, unsymmetrical ketone. Now see, this is an unsymmetrical ketone. In the case of unsymmetrical ketone, OH minus can extract from this position because it will try to make the enolate more stable. Okay. But LDA will try to extract the hydrogen which can provide more stable carb anion. So here, more stable carb anion is here because it is 2 degree. OH minus will take H plus from here because it can form more stable enolate. See, enolate is the direction of product, correct? Product will go in this direction. Carb anion is the direction of the intermediate, correct? And you know that whenever we say kinetically product, that means we are looking for a direction where the intermediate is more stable. Okay. When we say something is thermodynamically controlled product, that means you are saying the product is more stable. Girls, clear beta? So that's why if at all I have any bulky groups like LDA or tert butyl oxide, tert butoxide, okay, all of these will try to extract hydrogen from the less bulkier position, which will provide more stable carbanion. And that's why if you see in this reaction, LDA will take H plus from here, gets a negative charge. And that C minus is the one which will attack CH3I. Okay, that will attack this CH3 and you will get this product. But if it was with OH minus, see this OH minus will take H plus from here, gets a negative charge, and that negative charge is the one which will connect here. So you will get this as a product. Sorry, this side, this methyl is not there. Okay. Sorry, I have to, yeah, this one is correct. Right? Clear? This is how the reaction will take place. Girls, any doubt? Okay. So what are the alternative, you know, other bases? What are the other bases in this case? The other bases are tert butoxide, trimethylamine. Okay. These two are the cases where you will have a similarity. And obviously, this should favor with low temperature. Okay. And here, anything like H minus, D minus, R minus, HC triple bond C minus. Got it? And RO minus, NH2 minus, clear? NH2 minus, RCH double bond CH minus. So any of these bases, they all will favor this particular type of mechanism and normal to high temperature. Normal to high temperature is favorable for thermodynamic product. Done? So these are the cases you should look out for. Okay. So when to use KCP, when to use TCP. Okay. Next. How do we get to know halogenation happening at alpha position? See, if you have a keto group and you are conducting halogenation, right? If by chance there is a methyl group here, you will end up getting a complete haloform reaction. We discussed haloform reaction before in alkyl halides. Okay, so where we removed this complete carbon group, converted into an haloform, and rest of the part has converted into an acid group. Okay, but if you simply add it in the presence of water, nothing will happen. You need to have either in basic group or in acidic group. If you do the same thing in acidic medium means like this. You take Cl2 in the presence of CH3COOH. This is one example. Okay, if you have, that means chlorine is taken in acidic medium. In that case, you will see only one halogen has been substituted. Again, my recommendation is do not worry about the mechanism here for acids. So just as a note, remember that, okay, polyhalogenation, polyhalogenation is observed is observed in basic medium, but only monohalogenation at one alpha position is observed in acidic medium. So in acidic medium, only one halogenation. Even if you provide excess amount of chlorine, though excess bromine, you can give any amount, you will still get only one halogen adding, one halogen substituting. But in base, it is not like that. Base, all of them will be replaced. So this is a JE question. If bromine with NaOH is given, you will replace all four hydrogens with bromine. But if it is with acidic medium, you will only replace one bromine on both sides, one hydrogen on both sides. Clear, beta? Okay. Now let us talk about the oxidation reactions. Hmm. There are mainly four type of reactions which will oxidize the aldehydes into acids. The first one is shift test or shift base. Shift test, sorry, not base, shift test. Shift test is aqueous solution of a base which gets decolorized by passing SO2. Okay. Now notice this compound is called para-rosaline, which is a pink color liquid. Okay. Now when you add SO2 to it, it will convert into a reagent which is colorless. This is the reagent. Basically, on this double bond, you will see this carbon will come out as C minus, attacks on SO2. That will convert into SO3H here. Okay. So because first it will become, first sulfur will attack on it. The pi will shift like this. Clear? And thereafter, the sulfur has empty orbital on which water will attack, convert that into SO3H. Okay. And here also on this NH2, SO3, SO2 will get attached here this way. Hmm. So what you will get here is a Schiff reagent. This is called Schiff reagent. Schiff reagent is colorless. Now the minute you add it with an aldehyde here, correct? When you react that with an aldehyde here, this part of the sulfur, right, that will help in oxidizing aldehyde and it will be removed out. This part of the sulfur dioxide will come out as again SO2 and that will be removed out. The minute this SO2 is removed out, again it will start regaining its pink color. Understood now? And this aldehyde will convert into an acid form. Okay, and that's how you will notice that we will have an aldehyde converting into an acid form. Okay, this will become RCO, not minus COOH only directly. So this got oxidized. And mind you guys, this is the only reagent which is oxidizing aldehydes to acid in acidic medium. Rest all will do it in basic medium. Okay, clear with this point? Right. Now this is about aldehydes converting into an acid in acidic medium. So let me put it as a note here. Aldehydes, okay, converting into an uh, acid in the presence of para, okay, rosaline solution, para rosaline solution to convert that into an acid form. This is called shift test. Hmm? Next one is a ketone converting into an ester. Ketone can be converted into an ester, and that is called Baeyer-Villiger oxidation. This is called Baeyer-Villiger oxidation. Now you notice that this is a keto group, and if the ketone group is pushed with an uh, peroxy acid, this is a peroxy acid. In peroxy acid, the oxygen which is present, wherein the oxygen which is localized electrons, because these electrons are not delocalized, but here these electrons are delocalized by a resonance. So the oxygen, the peroxy oxygen which is localized, that will get inserted on any of the direction, converting into an ester. Okay, see how the mechanism proceeds. So first, the oxygen from here will attack on this carbon. As it happens, this oxygen will take H plus from here, you will get this form. And then when oxygen closes a double bond, the phenyl will shift from here and attacks on this oxygen, and thereby removing this O minus. And that O minus will take H plus, converting into an ester form. Okay. Now it all depends upon whether it is phenyl or whether it is methyl. Any one of them can migrate. So that depends upon the migrating aptitude. Now this is very different migrating aptitude from general cases. So better remember that. First is hydrogen, then it is 3 degree. Okay, right? No, no, sorry. Mm, yeah, correct. First is hydrogen, then it is 3 degree alkyl group. Then within 2 degree, remember that we have cyclohexane greater than cyclopentane, cyclobutane. Then we have phenyl groups. Then we have all the phenyl groups with donating groups, only phenyl with withdrawing groups. And then comes 1 degree methyl and RC double bond O group. So this is how the migrating aptitude is observed. Okay. Now if the ketones are present with both side, R group is present. In that case, if two ketones are present, means within the molecule only the insertion will take place and O will migrate here. This is an exception, remember it. So you will get anhydride instead of an ester. Now here this is a ketone. You react with any acid. Because both sides are same, any one direction you insert the oxygen, you will get a 6-membered cyclic ester. Okay. And this is alpha position, beta, gamma, delta. At delta position, we have an ester form. So that's why it is called delta lactone. Okay. All the cyclic esters are called lactones. Okay. Now this said there is methyl, this said there is ethyl. So ethyl has a better migrating aptitude. So propyl has better migrating aptitude. So you insert oxygen here. Okay. Hydrogen is there, methyl is there. Hydrogen has better migrating aptitude, insert oxygen here. So that's how you'll get acid. Okay. So have you noticed Baeyer-Villiger is also a case where aldehyde can be converted into an acid, just like shift test. Okay. But shift test is only given for aldehydes, but Bayer's reagent, Baeyer-Villiger oxidation is given for aldehydes as well as ketones. Done. Alternatively, instead of using this one, we can also use concentrated HNO3. Concentrated HNO3 will also make an insertion like this. And as you further react with it, it will open to convert into an primary alcohol and an acid. And the primary alcohol, if you keep on adding concentrated HNO3, that will get oxidized to acid. And this particular acid is called adipic acid. It's a very important acid in biomolecules. Adipic acid. Okay, right. The next reaction is with selenium dioxide. See, selenium dioxide, if you have only double bond, it will give you allylic alcohol formation, which is an oxidation as well. If you have an aldehyde, it will make the alpha carbon to also convert into an aldehyde. So that's how you can get glyoxal. If you have an ethyl group, you will get a keto form with an aldehyde. If you have two keto groups here, we can have the more substituted keto group to be major product. So this is dimethyl glyoxal. Hmm. Selenium dioxide will basically convert into a selenous acid, and it is that selenous acid which will react and convert that into selenium, which gets reduced into selenium, and rest will get oxidized into this form. This is just for your information. Nowhere the mechanism is asked to you. Okay, you see that if you have selenium dioxide in acidic medium, you just make a double bond O here. That's it. And do you remember, if you have a double bond O here and then you are using with NaOH and H3O plus, this is same as benzylic rearrangement. Remember that? So basically first you'll get OH minus attached here, then this group will go connect here. So it will become 5-membered ring. Hmm. Let me refer, I'll just put it here. Refer benzyl, benzyl, benzylic rearrangement reaction. Okay. Now, what are the other mild oxidizing agents? See, there are three important oxidizing agents. One is Tollens reagent, Fehling's reagent, and Benedict reagent. Hmm. Check out first one. If you take silver nitrate with ammonium hydroxide, it will convert into a complex known as silver ammonium hydroxide. This is a colorless solution. When you add it to an aldehyde, that aldehyde will convert into an acidic form, and this ammonia will escape out and silver will get reduced. Okay, 1 mole of aldehyde will reduce 2 moles of silver. Remember that point directly. Okay, 1 mole will reduce 2 moles of silver. So you will get a silver mirror forming on the test tube like this. On the walls of the test tube, you will see a silver mirror forming. And that is an indication that there is an aldehyde present here. Failing solution. Failing happens with two solutions. First, we have to take, 50% of aqueous copper sulfate in a test tube, which is called failing A solution. Then we take 50% of the tartaric salt solution, okay, which is called Rochelle salt. Rochelle salt is basically sodium potassium salt of tartaric acid. Okay, so 50% of this and 50% of this together, when you add, that will become a liquid solution, colorless one. Okay, basically it forms a very stable complex like this. First, copper will form a stable complex like this with Rochelle salt. This was a JE question asked. What is the coordination number of copper? Answer is 4. Okay. Girls clear beta. Right. Now, this complex, as it reacts with aldehyde, okay, aldehyde will get oxidized, copper will get reduced. The copper from here will react with aldehyde, reduces into a brick red precipitate, which is Cu2O. So if you get a brick red precipitate, that means there is an existence of aldehyde there. And these reactions are explicitly for aldehydes. They are not uh, observed for ketones or any other group. Mhm. Next one is Benedict solution. Benedict solution is just an alternative of failing solution, nothing more. Here also there are two forms of solutions. One is 50% of aqueous copper sulfate you have to take, and 50% of potassium sodium salt of citrate. This is the citrate molecule. Okay, clear? Potassium and sodium. So here one of them is sodium. Okay, so now what happens? You will see copper is getting connected with this one. Here also it is getting connected with this one. Here like this. Okay, with the other COH groups. So here also the coordination number of copper from 2 moles it will observe, and here also coordination number is 4. This is the complex which it forms. Now, once you get this complex here, this also when you react with an aldehyde, you will get a brick red precipitate. So it is nothing different, only the salt solution is different. There we are using Rochelle salt, which is uh, s- uh, tartaric acid. Here we are using citric acid. Girls clear? Okay. Now, in which case what reaction will take place? See, Tollens, Failings, Benedict, they will never disturb a double bond or a triple bond. First important thing. But if there is a triple bond at an terminal position, Tollens will give a white PPT, Failings and Benedict will give a red PPT. Okay, this is a silver salt of alkyl group, alkyne group. This is a copper salt of alkyne group. So this will give a red PPT, this will give a white PPT. Keep that in mind. Okay, next. If you have a hemiacetal, you know that hemiacetals are unstable in acid, sorry, in base. So in base it is unstable, so it will immediately convert into an aldehyde, and that will give a positive test with Tollens, Failings and Benedict. So everywhere there is a hemiacetal, it should be always read similar to that of an aldehyde and proceed. Okay, next. If you have a carboxylic acid, sorry, formic acid, formic chloride, or you will have an formic ester. In all of these, as long as this hydrogen is present, they can be utilized to be further oxidized to carbon dioxide. And therefore, it will give positive test with Tollens, Failings and Benedict. Clear, girls? These three will also give positive test. Next, if you have alpha hydroxy ketone, there is a keto group, but at the alpha position you have an OH group. In that case, the alpha hydroxy group will get converted into keto group here. Okay, and that is also going to get positive, Tollens Failings test. But here there has to have one alpha hydrogen. If there is no alpha hydrogen, then it will give negative test with Tollens Failings and Benedict. Okay, now notice sucrose, starch and cellulose, they all have acetal groups, and you know that acetals are stable in basic medium, and Tollens, Failings, Benedict, all of them are in basic medium. That's why sucrose, starch, cellulose, which is in a acetal form, they do not give positive test with Tollens reaction, Failings or Benedict solution. Next, glucose, fructose, mannose, galactose, lactose, maltose, all of them have hemiacetal form, and hemiacetals will give you positive test. So they all will give positive test with Tollens, Failings and Benedict. This is our next topic as we go towards biomolecules. Next topic. Then you will learn all of this again. Okay, you will come across all these reactions again with biomolecules. Clear? Next, this is a very interesting one. See, for Failings and Benedict, there is one important condition. The condition is if you have an aldehyde, right, on the alpha position, this is in alpha carbon, there must have an alpha hydrogen. Okay, this is an important condition for Failing and Benedict. But Tollens, it is not an important condition. It only needs to have an aldehyde. That's it. That's why if you take benzaldehyde, if you take glyoxal, in these two cases, alpha carbon, which is sp3 positioned, is not there in this case or this case. That's why Failing and Benedict give negative test, but Tollens will give positive test. So, girls, very important statement again. The only place where we can differentiate Tollens reactions with Failings and Benedict is when you react with benzaldehyde or glyoxal. Okay, understood? Right. Next, any acetal, this is an acetal group, will always give negative test with Tollens, Fehlings, and Benedict. If again this is a furfural, this is common name used, furfural, you will be using in biomolecules a lot of time. When you use furfural again with Tollens test, it is positive, but Fehlings and Benedict, it is negative. This is hydroxylamine. Any hydroxylamine will easily get oxidized to nitroso group, N double bond O. Okay, so this is a positive test for Tollens. It is observed for Fehlings and Benedict also, less observed, but yes, you can take the reaction. Okay, next one. Now, if you have this alcohol form, correct, especially for uh, this is called catechol and quinol. One second. See, if you have catechol and quinol cases, here it will give positive test with Tollens, Fehlings, and Benedict, but only in cold condition. Okay, but if you have it in this case here, right, this will give a positive test, which is this is called resorcinol. Okay, name is resorcinol. So with resorcinol, you will get positive test with Tollens, Fehlings, and Benedict. Okay, similar to resorcinol, we have uh, you know fluoroglucinol. This is called fluoroglucinol. Clear? So fluoroglucinol will also give positive test with Tollens, Fehlings, and Benedict. Okay, beta. So you got to go through these cases, guys. You need to know in which cases you will get positive or negative Tollens, Fehlings, and Benedict test. Okay. Next, if you notice strong oxidizing agents, for example, if at all I take KMNO4 in acidic medium, KMNO4 in basic medium, K2Cr2O7 in acidic or basic medium, acidic medium. Hmm. You take concentrated HNO3 or CrO3H plus H2CrO4. These are all various representations of strong oxidizing agents. With strong oxidizing agent, you will see aldehyde will convert into an acid group and ketone will break down because ketones in strong or here strongly heating will have more enol existence, and here the bond breaking will take place and it will convert into respective acids. If it is a single carbon will always convert into carbon dioxide. Done, beta? Okay. This is what happens with strong oxidizing agents. This will discuss the same in alcohol also. Okay. Because alcohol's oxidation will first convert into aldehydes and then convert into acids. Okay. Next, last thing is about reduction reactions. Suppose if I want to convert ketones directly into alkanes, then Clemenson's reduction, Wolff-Kishner reduction, Mozingo reduction, or red phosphorus HI. These are used. If I want the ketones or aldehydes into alcohols, lithium aluminum hydride, NaBH4, H2 nickel, Raney nickel, sodium in ethanol, Bowald blank reduction. These all we discussed as a preparation reaction in alcohols. Hmm. And next, if you have a ketone and an alcohol, with Clemenson's reduction, this ketone will get reduced, as well as this alcohol will also get reduced, sorry, directly into alkanes. With Clemenson's reduction, even this part will get reduced into alkane. With Wolff-Kishner, the alcohols will not get disturbed. Hmm. Lithium aluminum hydride, it will reduce this one as well as nitro group. So this is the product. Sodium boron hydride, it cannot reduce nitro, but it can reduce keto group. Okay. With H2 and H2 palladium or nickel, it can reduce nitro group as well as keto group. So that's why you'll see these two groups got reduced. Done. Girls, clear on that? Right. The last thing is about conjugate addition. Conjugate addition is simple. I mean, I would suggest you remember it in a more simpler way, that wherever we have any conjugate, if you have a negative charge which is under conjugation like this, you can see this is under conjugation. Here, this is under conjugation. Correct? This is also under conjugation. Right? If you have that kind, or anything which is a weaker nucleophile, these are all relatively weak nucleophiles. If you have a weaker nucleophiles, wherein the carb anion is conjugated, or they are connected with strong metals like copper or cadmium, right? In all these cases, the addition happens at 1,4. But if you have strong nucleophile, like only RMGX, lithium aluminum hydride, sodium boron hydride in CCl3, RLI, they all will give you, addition at 1,2 position. Okay. If you are making a 1,4 addition, if you are making a 1,4 addition, that is called Michael's addition. 1,4 addition is always called Michael's addition. Let me show you this reaction, for instance. Okay. Ethoxide can take H plus from here. So what are we generating? We are generating a nucleophile. So this is a nucleophile which we generate. So you can see this nucleophile is a weak nucleophile. And now here there is a conjugated ketone here, right? On a conjugated ketone, these are the names which we'll write. Okay, this is position 1, 2, 3, 4. Okay. Now, what I would see that when it is a weak nucleophile, the addition happens at fourth position first. So this will be pulled here and this will be pulled above to get O minus. So what is the product? This is how you will get with O minus, and this carbon is connected here to this new carbon. Clear? And double bond got shifted between 2 and 3. And this is position 1, 2, 3, 4. And this carbon is now connected with a carbon which already has a double bond O methyl, double bond O methyl. Okay, let me mark that carbon for your reference. This is the carbon I'm talking about, which got connected here at 1,4 position. Done, beta. So in water, this O minus will take H plus and convert into this enol, and enol will convert back into ketone. Now this addition is called 1,4 addition, guys. Understood now? So every 1,4 addition is typically called as Michael's addition. That is called Michael's addition. And this is noticed in aldol condensation also. And that is called Robinson annulation. This is called Robinson annulation. Let me show you how. OH minus will take H plus from here. You get negative charge. You know that negative is resonance stabilized, which means it is a weak nucleophile. And weak nucleophile favors 1,4 addition. So it will go attack here, pi will shift here, this pi will shift here, right? Once the pi shifts here, that O minus will again get back to keto form. I have directly written the product. Now there are two ketones internally. So if you have internally diketones, I can convert that into intramolecular. This is intra-aldol. So we'll have an intra-aldol form. So which means from this CH2 minus, directly it can attach here. So that will lead into 6-membered ring. And on heating, this OH and H will go away, double bond will form. So we'll get condensed aldol. Girls, clear? So remember, Robinson is an aldol condensation followed by Michael's addition. Aldol condensation followed by Michael's addition. Okay, let me write down that statement also here. Michael's addition followed by aldol condensation. This is called as Robinson annulation. Okay. Next, if you have HCl in the presence of NaCN, okay, if you have HCl in the presence of NaCN, if you are taking at a very low temperature, at low temperature, kinetically favorable product is observed, which is 1,2 addition. Okay. If it is at high temperature, thermodynamically favored reaction is observed, which is at 1,4 addition. So 1,4 addition is always thermodynamically favored product. 1,2 is kinetically favored product. Okay. If only HBr is given, you will do simply 1,4 addition here. Okay. Okay. You'll only get 1,4 addition here. Okay. Like this. So you can see first oxygen will take H plus, then bromine will attack from here. This is how the shifting will take place. Okay. So you can see what is the order of conjugate addition beta. The first addition is always about amides, then esters, then ketones, then aldehydes, then acid chlorides. I would suggest do not worry too much into the mechanism and theory behind it. For these cases, more than anything theory, you just need to remember when to use 1,2, when to use 1,4. That's all. If you know that information, that is good enough. Clear? See, whatever I've discussed is more or less every case that is asked in advance as well. Okay. But in the recent time, Robinson annulation was asked in JEE mains as well. So that's why it's better to understand this case. This is a direct question, by the way. This is the same question asked in JEE mains. So remember what is Robinson annulation, how it is been done. And Grignard's reagent additions are being usually asked always. So Grignard's without copper salt it is 1,2. With copper salt it is 1,4 addition. Done beta. Right. Okay. So this is all what you have it from second part of aldehydes and ketones. Clear? So more than anything, you need to now sit and complete all the reading part. Clear?